Hello, I am Anton Vetlugin, a postdoc at Nanyang Technological University, Singapore, and together with my colleague Rusian Guo, under supervision of Cezar Sochi and Nikolai Zholodev, we study quantum phenomena in coherent absorption, and recently we found that it may be used for efficient entanglement generation in quantum networks. Let me remind you that quantum network consists of nodes connected by quantum channels. Here you can see a few practical realizations of quantum networks, and the quantum network can be built from atoms, from ions, or for instance from color centers in solids. And quantum networks are important because they form the basis for numerous applications, such as quantum computation, quantum communication, and so on. Quantum network by itself is useless unless we are able to generate entanglement in the network. And here I give you an example how the entangled state may look. And it is a single excitation, which is coherently distributed between the nodes of the network. For instance, the first term of this state describes the first node in the excited state and all other nodes in the ground state. The second term describes the excited second node and all other nodes in the ground state, and so on. How these states are generated. So here I compare two approaches. One is conventional parallel approach, and one is the approach we propose, the series approach. So in the first one, the single photon is split on a series of beam splitters into multiple optical modes, and each optical mode is independently mapped onto the corresponding node of the quantum network. The problem with this approach is it's not efficient if the network is large. So here I give you an example. So if you have the probability of mapping of optical mode onto the node of the network of 90%, and we have 100 nodes of the network, so the required state we are trying to generate here will be excited with probability of somewhat negligible number. So this approach is not scalable, and it requires strong light-matter interaction in each node of the network. So in our approach, we avoid splitting of single photon into multiple optical modes, and we arrange it in a way that the entire network interacts with a single optical mode. And as I'll show later, this approach is efficient, it is scalable, and it requires weak light-matter interaction in each node of the network. Our approach has its roots in the phenomenon of coherent perfect absorption. So let me briefly describe this phenomenon. The input light is split into two beams, and these two beams are counter-propagated. In the middle of the interferometer, the standing wave is formed, and I schematically show the standing wave here. So it has its antinodes, where electric field is strong, and nodes where electric field is always zero. And on the right-hand side, I simulate this process where we send the two traveling waves in the counter-propagating geometry, and the standing wave is formed with electric field oscillating up and down at the antinodes, and with electric field always equal to zero at the nodes. Now, if we plate the absorber, and we keep in mind that later we want to replace the absorber by the node of the quantum network. So if we place the absorber at the antinode of the standing wave, and by properly tailor the optical response of the absorber, we may achieve the regime of total light absorption. So as it can be seen from this simulation, so again we counter-propagate two traveling waves, but now we put the absorptive layer in the middle. And as you can see, that only input traveling waves propagate towards the absorber, and we don't see the outgoing light at all. And in this formulation, we assume that the absorber is thin, which means that it is smaller than the optical wavelengths, so we may define its location relative to the standing wave. The phenomenon of coherent perfect absorption was introduced in these two papers by Chong, Chow, Stone, and colleagues. Later, in the group of Nikolai Zholodev, the regime of coherent perfect absorption with a thin absorber was introduced. And these kind of absorbers were used in coherent absorption with quantum light, for instance, in the group of Faccio and Coutier, where our group contributed as well. And here are the latest experimental results from our group, where we managed to control single photons by coherent absorption in quantum networks, and we demonstrated coherent absorption of entangled photons. From theoretical point of view, this problem may be traced back to this paper of Loudon and colleagues. And recently we developed a unified description of this phenomena for different quantum states of light. In this talk, we extend this phenomena to the regime of distributed coherent perfect absorption, where we split the single layer absorber into multiple layers. And we keep in mind that instead of absorbers, we may use nodes of the quantum networks. So for instance, on this slide, we use two absorbers placed at two separate antinodes of the standing wave. And when we simulate this system, we see that again only input light is presented and we don't see the outgoing light. And here we simulate distributed absorber consisting of 7 absorbers, where each absorber is placed at different antinodes of the standing wave. And again, we are able to achieve the regime of total light absorption. And what is important that the more absorbers we use, the weaker light absorption in each layer is required. And if we think of this system as of the quantum network, this would mean that the weaker light-matter interaction in each node of the network is required to achieve total single photon absorption by the network. So as I told before, we assume that absorbers are of a sub-wavelength thickness, but actually it's not necessary, and the regime of light absorption may be achieved in thick media as well. But what we like about thin absorbers is that we may easily access the regime of coherent transmission. So now if we place these thin absorbers or thin nodes of the quantum network at the nodes of the standing wave, the electric field is always 0. Light simply does not interact with these absorbers, and as you can see, the nice standing wave is formed. And this standing wave is exactly the same if we just remove the absorptive layers. So which means that in this regime the light is totally transmitted by the absorptive layers. And this nice feature to be able to modulate the system between the regime of total light absorption and total light transmission may be of interest for instance, for feed-forward protocols of quantum information. This is our experiment where we demonstrate efficient coupling of a single photon to a basic binodal structure. We generate photon pairs through spontaneous parametric down conversion, where one photon from the pair is directly sent to single photon detector, and it heralds the presence of the second photon from the pair, which we send to interferometer, and where it stands, it forms the standing wave in the middle of the interferometer. And the position of the standing wave is controlled by this fiber stretcher, and by changing the phase, we may shift the antinodes of the standing wave relative to the absorber we use. So the outgoing light is detected by these two single photon detectors. And in the experiment, we measure the probability of photon absorption through the coincidence counts measurements between this heralding detector and these two detectors as a function of the phase applied by fiber stretcher. And the binodal system we use consists of the transparent substrate and two thin absorptive layers. So these absorptive layers are tailored to have the required optical response, while the thickness of the substrate allows us to put these absorptive layers at two neighboring antinodes or nodes of the standing wave. So in the experiment, we measure the probability of photon to be detected at this single photon detector or this single photon detector, these blue and red curves, as a function of the phase. And if we sum up these two curves, we get the probability, the total probability of photon transmission through the binodal structure. And if we reverse this curve, we get the coupling efficiency, total coupling efficiency of the photon to the structure. And as you can see, the highest probability we achieved is 88%. And if we compare with the efficiency which we would achieve in the parallel approach for these parameters of the structure we use, so you see the very nice enhancement of the absorption probability. Here, let me briefly elaborate on the practical realization of our approach with quantum systems. First of all, I should say that periodic arrays of atoms and ions are widely studied worldwide. And this arrangement is very close to the arrangement which is required for our approach. Next, for instance, in the group of ABI, they know how to precisely locate the protons, so in these centers, with this precision of tens of nanometers, and that is good enough to be used in our approach. And finally, these days I ran into this nice talk by Nandi, where they use periodic layers of ions in the crystal to study the phenomena of coherent backscattering. And again, this arrangement is very close to what is required for our systems. On this slide, I show you theoretical analysis of the periodically arranged quantum systems. So where each node of the system is characterized by its own amplitude, and we have two light modes coming from the right and coming from the left. And similar, we have the output state of the system, and these two are linked through the scattering matrix S. So we write down this transformation in the matrix form, and we claim that all the outgoing light is cancelled, both from the left side of the system and from the right side. And we show that the resulting state of the network is indeed the entangled state, and this state is the state which I showed you on the very first slides of this presentation. In conclusion, we demonstrated new scheme of entanglement generation in multinodal quantum network, which is at the same time efficient, scalable, and requires weak light meta-interaction at the nodes of the network. And it has the nice property that it can be modulated between the regime of total absorption and total transmission. And we experimentally demonstrated efficient single photon coupling to the basic binodal system. And here let me advertise you to more talks from our group. And thank you for your attention.